Alright, welcome back. So today we are looking at section 3.2 and some properties of determinants. This is the penultimate section in chapter 3. And the next thing we're going to look at is Cramer's rule, which some of you might have seen before, but we'll talk about it a little bit. So you might also be wondering, what are determinants helpful for? Well, one of their applications is, and it's pretty cool, you should look into it for a journal, is finding volumes of crystal shapes. So like tetrahedrons, which are, when you have like this and then like that happening. So it's kind of more like a triangle thing. Or parallel pipeheads, which are where you take a parallelogram and then you like extrude it out. So that all the faces are parallelograms, and please excuse my pretty bad sketching. So parallel pipeheads, you can find the volume of that using determinants as well, which is pretty cool. And I mean, just like taking that back a step, you can also find, areas of parallelograms, using determinants as well. So what are some properties of determinants? Let's look at that. So, if you have a square matrix and, you're doing row operations on it, then, some of those row operations change your determinant and some of them actually don't, which is pretty cool. So if you take a row and add it, multiply it and then add it to another row, if you're doing, if you're doing row reduction, then that actually doesn't change the value of your determinant. But if you take two rows and you swap them, so like row 1 and row 2 switch, then you change the sign of what your determinant is going to be, because and if you think about like our cofactor expansion, when we had that the -1 to the ij power, when you switch the rows, you change that around. So when you have interchanged rows with your elementary row operation, if you're interchanging rows, then your determinant is going to be the negative of what your original matrix's determinant is. But if you do two row swaps, then you cancel it out. You have a negative of a negative. And if you have a scalar multiple, then your determinant, you can just scale that out. You can take that scalar out and then multiply it at the end after you figure out what your determinant is. So like if you had A, B, C, D, E, F, G, H, I, but then you had, this was like K of that, that's the same as if you had this K distributed everywhere, that determinant. So, let's try an example. So pause the video, try this out, thinking about all the properties that we have. Determinant of this matrix A, we can actually take our first row, multiply it by 2, and add it to our second row. So we have 1, -4, and 2, and then we get 0, 0, and 2 is 4. 4 is -5. And then we have, we can do this in one fell swoop, right? We can add this as well. So we have 1 plus -1 is 0, and we get 3 and 2. So we took a multiple of a row and added it to another row. Okay, so that means that our determinant is still going to be the same. And if we swap, let's see, these two, right? Because then we end up with a triangular matrix. Then we have to negate what our value is. And then we have 1, -4, 2, 0, 3, 2, 0, 0, -5. And here we have triangular. So we end up with 1 times 3 times -5, and then negative of that. So negative 15 is positive 15. So our determinant here, determinant of A, is positive 15. A common use of this last part, where we're factoring out our scalar, in our hand calculations, is to factor out a common multiple of one row, and then you are you're good to go. That your determinant here and your determinant here, they're the same. So let's look at the determinant of A when we have this 4x4 matrix. So we should use some row operations. So pause the video, think about it, how you're going to do that, and then we'll talk about it. Here, when we let's look at our first row, right? We can have we can have a 2 factored out of that, so we end up with a 1, negative 4, 3, and 4 with a 2 multiplied out here. So that was that trick from what we were talking about before. And so now we can go through and we can do our multiple of like row 1 and add it to another row. And so that doesn't change our determinant. So what do we end up with? We end up with 2 times 1, like that. And then let's go through and zero out everything else. What do we end up with? We got 0, 3, negative 4, and negative 2. We get 0, 12, negative 12, 10, and 10. And then we end up with, those are the same, 0, 0, and we get, what, negative 3 and 2. And so from here, well, that's kind of nice. We could also, is there anything we can do from row 3? We can factor that out. So then we end up with what? 2 times 3 is, 2 times 2 is 4. And then, what else do we have? We have 4 times our determinant. negative 4, 3, 4. 0, 3, negative 4, negative 2. 0, and then we factor that 2, right? So then we have negative 6, 5, 5. And then 0, 0, negative 3, 2. Okay, looks like we can zero out something else. So what do we get? We get 4 times 1, 3, 4. 0, 3, negative 4, negative 2. And let's move that over. And then we get, what we get? 0, 0, 2 times 4, negative 3, 2 times negative 2 is negative 4 plus 5 is 1, and then we get 0, 0, negative 3, 2. Okay, now we're getting somewhere. We got these negatives that we can, or negative 3s that we can add together, so we get what? 1, negative 4, 3, 4, 0, 3, negative 4, negative 2, 0, 0, negative 3, 1, and 0, 0, 0. The difference here is that like negative 1 plus 2 is 1. Okay, and now we have triangular, so now we can multiply through, and we end up with what? 3 times 3 is 9, negative 9, times 4 is negative 36. So there you go. There's your determinant. Cool. I'm very relieved that matched with the book. And so we looked at this before a little bit, thinking about like what happens when we have triangular matrices. So if you have non-zeros, only non-zeros on your diagonal for a triangular matrix, then you have your determinant is non-zero, which means that you have enough pivots. You have the right amount of pivots for making sure that, you know, your matrix is like fully defined in terms of its, like it can be inverted, right? Because we have enough pivots, we have a pivot in each column. So our determinant is negative 1 to the r power, which is like some number, times the product of the pivots in, then this power is like the number of rows, times the product of the pivots. So you just take that, multiply. And then that means that your matrix A is invertible. But if you end up with a determinant of 0, so if you have like a echelon form, but you don't have enough pivots, then you end up with a 0 as your determinant. And so that shows that your matrix A is not invertible or it's singular. And so I think that means that we can add something else to our invertible matrix theorem, that we have a square matrix is invertible if and only if, so it's equivalent to if our determinant is non-zero. So we sneak that in to our invertible matrix theorem, where we have an invertible matrix, which is all these things. Our transpose is also invertible, which we're going to look at determinant transposes later. and our determinant of A is not equal to 0. We have a non-zero determinant for A. And that means that we also have enough pivot positions that we have the same number of pivots as we have rows, and we have columns that are linearly independent, so these are all saying the exact same thing. This example, let's try to pause the video, think about how you're going to do this. Is this determinant, what is this determinant? So pause the video, think about it, and then we will work on it. So, what happens when we look at determinant of A? Oh, that's a hard color to read. Determinant of A. That's going to be, we have 3, -1, 2, -5, 0, 5, -3, -6, 0. Let's see, 3 times, 2. So then we get 2, and then we got a 5 here. We get 2 times 2 is 4, -3, 2 times -5 is 10, so we get -6, and then we have 5, -8, 0, and 9. And so look, we have row 2 and row 3 are the same, so that means that we're going to end up with, like if we just take that row and add it to, if we take row 2 and add it to row 3, then we end up with a row of zeros. We don't have enough pivots, so our determinant, and this matrix is not invertible, so our determinant is 0. Alright, so we quickly so just think about some numerical things that our computer programs, they tend to compute determinants of A for using this formula, using this in here. And you can also think about how many like flops it'll take, which is fun, I guess. That when you're looking at an n by n determinant, then you can do this in 2 times n cubed over 3 flops, and that's pretty good. It might be interesting to time how long it takes to compute a determinant, just for fun. All right, let's look at this example. So pause the video, try to do this, compute this determinant, keeping in mind all the things that we've talked about. Alright, so for this example, what do we need to do? Well, we can take, okay, so we can deal with that, probably just get rid of that last row, right? So then we have determinant of A equals our determinant here of what? 0, 1, 2, -1, 2, 5, -7, 3, and 0. Oh, 0, lovely. And then we get what? -3 and 1. Okay. And then can we use row 1 times -3 plus row 3? So then we end up with zero, 0, 0. The -3 times -1 is 3 plus 2 is 5. 0, 0, -3, 1. Okay. And then if we just do some swaps of our rows, then we're going to end up with something that we can just deal with by taking our triangular determinant, right? Because we can take row 1 and swap it with row 2, and then row 3 and swap it with row 4. So we have 2 swaps, so negative, negative, and that gives us just the same thing again. And so we can take these and we can change the order around here. What if we did this? With this from our swaps, we have triangular, so we can get just 2 times -3 times 5, and that's going to give us -30. So there's our determinant. We've got a couple other things. We have the determinant of A transpose is equal to a determinant of A. So when you're transposing, it doesn't matter. And that makes sense, right? Because when we're doing our determinants with our cofactor expansion, it doesn't matter if we're doing rows or columns. We're going to get out the same thing. So A transpose's determinant is the same as A's determinant because you're just going across a row versus going down a column. It's all the same. And then if we have two matrices that are multiplied together, the determinant of their product is equal to the product of their determinants. So I'm going to look at justifying that through some stuff in our problem set. We had some properties that we got when we were looking at products of matrices, and we can take their determinants separately. We have transpose's determinants is the same as our original matrix. We can do some elementary row operations, and we can appropriately change what that would, we can use those to our advantage for when we are calculating our determinant, because then we don't have to do as much work, which is really nice. So doing row swaps is the negative of the unswapped determinant, and taking a multiple of one row and adding it to another doesn't change our determinant. And then we have 0 for our determinant when our matrix is not invertible. If you think about flops, it's fun. Computing this is also nice because then we can see we can determine when our matrix is has a determinant of 0 based on if it's invertible or not. We added another thing to our invertible matrix theorem for the determinant has to be non-zero in order for a matrix to be invertible. And we had our triangular matrix property, which is really nice. We need the right number of pivots in order to do that. And that about does it. We have, oh, and then we will look later a little bit at some applications for why determinants are helpful. And it would also be, a pretty interesting journal entry. All right. Bye.